When we draw the final 8-bit register, we typically do not draw all the internal flip-flops, and we also rearrange the inputs and outputs to facilitate reading. So, in this lecture, I demonstrated the basic functionality of flip-flops, and I demonstrated how we can combine flip-flops to create a register. This process of abstracting the structure of smaller components to create larger components is called modular design. Modular design is one of the most important concepts in computer engineering. You should always look for opportunities to build more complex tools from several
A computer's registers each store the same number of bits. When we want to manipulate what is stored in these registers, the register file will be instructed to send the contents of 2 registers to the ALU. In this example, the registers are 8 bits in length. The ALU will perform a calculation on these 2 values and send the result back to the register file to be stored. We tell the ALU what instruction to perform by sending it a set of control bits that encode a message of what operation to perform. Because the ALU is a combinational circuit, it will perform these calculations immediately. To simplify the diagram, we will use a bus notation where we group sets of wires together and indicate how many wires are in that group. Rather than draw 3 sets of 8 wires, we will simply draw 3 buses. An ALU can perform whatever arithmetic operations that we know how to implement, such as addition, subtraction, multiplication, as well as decrement and increment operations. Bitwise logical operators, such as not, and, or, and others, comprise a list of non-arithmetic operations, such as value comparisons, and setting a register's contents to 0. The details of these operations are covered in another lecture. Suppose that we have an ALU that receives 2 control bits. Because there are 2 control bits, we can encode 4 operations for the ALU to perform. I've chosen 2 arithmetic operations and 2 logic operations for this example. The ALU receives inputs from 2 8-bit registers and sends out 8 bits of information back to the register file. Based on the data from the control bits, the ALU knows which operation to perform. In this situation, the ALU calculates the sum and sends it to the register file. If we change the control bits, we will change which operation is performed. Because this operation does not need an input from B, the B inputs will be ignored. The ALU will send an incremented value of A back to the register file. To briefly introduce the logic operations, we will examine one of the simpler operations, such as the NOT operation. The NOT operation receives only one set of inputs, so again, the ALU will ignore the inputs from B. The NOT operation changes all 0s to 1s and all 1s to 0s. The NOT operation is applied to each bit in the register individually, otherwise called a bitwise operation. Finally, if we change the control bits again, the ALU will perform a clear operation, which means that we will set the contents of a register to 0. For this operation, the ALU ignores both inputs and simply sends out the value 0. Notice that the ALU is sending out 8 zeros, because all numbers, even 0, are encoded with the same number of bits in a computer. In this lecture, you saw that an ALU receives information from the register file and then performs operations on this information. The control bits encode information about what operation the ALU is to perform. These operations will either be arithmetic operations or
So now let's briefly take a look inside the CPU itself to see how it would process an instruction. As we saw earlier, this is the inside of the 6502 CPU. Let's take away the 6502 wiring and see what's inside the Scott CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary